Given f of x is equal to this, find the critical points in the intervals where the function is increasing and decreasing. So this is a review of what we did yesterday. So the first thing I have to do is find f prime of x, and this is a super easy one, 4x cubed minus 12x squared. And I want to know my critical points. So I need to know, where is the derivative equal to 0? So I'm going to take out the GCF, and I have my critical points are 0 and 3. Okay. So the only place where we can change from increasing to decreasing are the critical points. So we want to know what's happening to the left and to the right at each of these critical points. So at 0, I can see that it's x squared here, so I know that it's probably not going to change signs, but let's go for it. If I plug in -1, I have positive times a negative is a negative. And if I plug in +1, same thing. So it's negative, negative. And my guess is if I plug in 4, something to the right of 3, yep, positive. So I am increasing from 3 to infinity. And I am decreasing from negative infinity to 0 and 0 to 3. I'm not doing anything at 0. Something's happening there, and that's what we're going to get into today. But I can't just say from negative infinity to 3 that I am decreasing. So what is happening at 0? I kind of told you guys the other day how it's called a point of inflection, but we're going to get a little bit more into that. I know I'm not asking for any maxes or mins, but just to talk about what's happening here, we're decreasing, and then we switch to increasing. So at this point right here at 3, we have a relative min. I know that was not asked of us, but I felt like saying it anyway because, I don't know, I like talking about stuff like that. I find this fun. So if we look further on in the note sheets, it says now do the same procedure with the second derivative. Use the graph to come up with an idea about what these intervals represent. All right, so let me go back. F prime was 4x cubed minus 12x squared. So f prime of x was 4x cubed. I already forget what I said. Minus, I'm looking at the answer key right now. Minus 12x squared. So f double prime is the second derivative. So that would be 12x squared minus 24x. So it says do the same procedure. Okay, so these are the critical points of my second derivative. Now, just so you know, whenever you're asked about critical points, it's always being referred to the first derivative. So you have to be really specific if we're talking about the second derivative. So I call these every single time the critical points of my second derivative. So people know what I'm talking about. Because if you just say critical points, it is assumed that you're talking about first derivative. So if I take out 12x, I'm left with x minus 2. So the critical points of the second derivative are equal to 0 and 2. Well, let's do a sign chart and let's see what happens. So it's 0 and 2. Now I want to plug numbers to the left and to the right into my second derivative. So if I plug in -1, I get negative times a negative is a positive. If I plug in +1, I get positive times a negative is a negative. And if I plug in +3, I get positive. So let's take a look at the graph and try to figure out what the heck is happening at these points. Because this is not maxes and mins, right? So this is the graph of f right here. This is the graph of f of x. So let's see what's happening. Ooh, pen, stop. All right. Oh boy. All right, let's try this again. All right, so at 0, I'm right here. And at 2, I'm right here. I wish we were together right now. What is happening here? Okay, so the critical points of the second derivative, they mean something. And I told you guys the other day that it's called a point of inflection or an inflection point. You've definitely heard this phrase before, and you just might not know what it is. So at an inflection point, the function's concavity changes. So we can be concave up, and we'll talk about what this means, or we could be concave down. And I think you guys probably know what that means already. You just didn't know really how to find it. So the second derivative tells us about the function's concavity. If you are positive, if the second derivative is positive, that means you are concave up. So notice here, I always say to determine concavity, I say take a cup of water and pour it on the function. If the function could fill up and hold some water, it's concave up. But in between 0 and 2, we are concave down. If I poured some water on here Is the function going to fill up? No. The water has nowhere to go because this is facing down. It's opening downwards. It's concave down. And then same thing here, from 2 to infinity, we are very clearly concave up. We could fill this up with some water if we had a cup and we poured it in. So that's what concavity is. And I have a picture on the next page that I'm going to show you guys, but I wanted to show you here. So that's what the second derivative tells us. It tells us where the function is concave up and where the function is concave down. So first derivative tells us increasing, decreasing. Second derivative tells us concave up, concave down. So if you look here, this is a much more accurate picture of concave up and concave down. So concavity is completely independent of increasing and decreasing. You could be increasing in concave down. You could be increasing in concave up. It's not like they have to go together or anything. And the point of inflection is the point where concavity changes. Okay, so if I go back, inflection, I spelled that correctly. If I go back all the way to the do now, the function didn't change from increasing to decreasing at 0, but there was something special going on at 0. Well, now we know what that special thing was. The special thing that was happening at 0 was that the concavity was changing. So was the derivative equal to 0? Yes, okay. But the second derivative was also equal to 0. And that is the point of inflection where the concavity changed. It changed from concave up to concave down. Very important to note, okay? So a lot of times when I'm finding a max and a min, we're looking for maxes and mins, and this doesn't change here, I'm like, oh, that's an inflection point. And, you just go further to figure that out. All right, did I forget anything else? So in order for a point to be a point of inflection, the concavity must switch, okay? So if this is a second derivative here and I have 0 and 2 and this is still positive, it's not an inflection point. Okay, it's only an inflection point if the concavity changes. That's a very important thing. So not everywhere where the second derivative is equal to 0 or does not exist is an inflection point. You need to have concavity changing for this special point here to be called a point of inflection. All right, let's try one. So we're given the function. Now we're asking for a lot. Find the critical points, the intervals where we're increasing and decreasing, the second derivative critical points, the intervals for concave up and concave down, and any points of inflection. Oh my God, does this just sound like the most fun problem ever? Let's do it. F prime of x is equal to 4x cubed plus 6x squared. Okay, and f double prime is equal to 12x squared plus 12x. Okay, so let's do first derivative over here. I want to know where the first derivative is equal to 0. 4x cubed plus 6x squared. I take out my GCF of 2x squared, and I'm left with 2x plus 3. So I have critical points at 0 and negative 3 over 2. So hopefully we're noticing right now, since it's x squared, my guess is that this is probably going to be an inflection point, but let's take a look at the sign. Okay, so now my work is getting a little more complicated. So next to my number line, I just make a note to myself that this is the first derivative. So I have negative 3 over 2, and I have 0. So if I plug in negative 2 into the first derivative, that's positive, but that's negative. So that's negative. If I plug in negative 1, positive, positive. If I plug in positive 1, very clearly positive. Okay, so at this point, I'm decreasing, and then I switch to increasing. So this is a relative min. I'm actually not asking me for the mins and maxes, but we do know that there's a relative min at negative 3 over 2. I know that I am increasing from negative 3 over 2 to 0, and then from 0 to infinity. My kids might come in the house right now. They're outside playing. And then I'm decreasing from negative infinity to negative 3 over 2. Okay, so let's check off what we did. We found the critical points. We found the intervals for increasing and decreasing. Now let's find the second derivative critical point. So that's going to be 0 is equal to 12x squared plus 12x. That's going to be x plus 1. So I have second derivative critical points at 0 and negative 1. So you can see we knew something special was happening at 0 here. So let's take a look. I'm going to just label this number line. Just, keep everything clear for myself. It's not something that's required of me, but I want to keep my work straight. Okay, so if I plug in -2 to the second derivative, negative is a positive. If I plug in -1/2, that's negative times a positive is a negative. And if I plug in +1, that's positive. Okay, so I am concave up where the second derivative is positive. So that's -infinity to -1 and from 0 to infinity. And then I am concave down from from -1 to 0. Where do I have inflection points? So my points of inflection take place at x equals -1 and x equals 0. And I know that these are inflection points. I'm just circling that because it's right smack in the middle of everything, because the concavity changes at these points. If one had stayed, if the sign did not change, it's not an inflection point. Okay, so this is a little annoying that I'm getting rid of my work right now, but I want to look at this. This is the graph of f of x. So let's talk about increasing, decreasing first. We said we were increasing from -3/2 to 0. Yep, from -3/2 to 0, we are increasing. And then we continued to increase, right? From 0 to infinity. Perfect. So we were decreasing until we got there. So our increasing and decreasing is perfect. And our concavity. So our concavity, we said we were concave down between -infinity and -1. Between -infinity and -1. Oh, is that what we said? No, concave up. Oh, goodness. I got a little scared for a second. Concave up between -infinity and -1. So here's -1, right? And you can see that is the magic point, guys. Look at what happens on that graph. Concave up, concave up, concave up. I get to -1, and all of a sudden, I'm concave down until, I think we said 0. Did we say? Yeah, we definitely said 0. Until this point right here. And then all of a sudden, I'm concave up again. Guys, this is craziness. We did not have access to a calculator, and we know exactly what this graph looks like. We know all of its special features. This is insane. So did I do everything? Second derivative, critical points, intervals for concave up, and points of inflection. I technically could plug those back in and get the actual values for those points of inflection. So let's see. That would be, if I plug in -1, that's 1 minus 2 is -1. So that's -1, 1, and 0, 2. Let's see if that was correct. So -1, 1, and 0, 2. Perfect. Okay, so that's everything that was being asked of me. So I'm at 13 minutes right now, guys. I think I'm going to have you guys do this one. Oh, no, don't cheat. Actually, you guys don't have this on your notes. Maybe you do want to look at this right now, or take a screenshot of it. Darn it, the second derivative test. I'm just going to have to make a second video. I'm going to keep going. I'm not going to do that one with you guys, though. I'm going to let you guys do that one, but let's quickly talk about the second derivative test. If the second derivative, all right, so if x equals c is a critical point on the first derivative, and then the second derivative of that point is negative, it's a maximum. If the second derivative of that point is positive, it's a minimum. And then if it's equal to 0, it's inconclusive. All right, so let's talk about this. So the second derivative test is an alternate way to classify max and mins. I honestly never use the second derivative test. It's not worth it to me because it fails you sometimes. If the second derivative of that point is equal to 0, you still don't know what it is, if it's a max or a min. So I don't really like the second derivative test. I think it's more work, but it is something that exists. So it's a critical point on f prime, and then you plug it in. So if the concavity is, if the second derivative is negative, you're concave down, which means it would be a maximum. If the second derivative is positive, you're concave up, which means it would be a minimum. So just kind of picture that in your head. But again, then you come across this situation and you don't know. So I prefer the first derivative test. That's just that's a preference. And I've never actually met someone that likes the second derivative test better. It's just some mathematician came up with this and probably wanted their name known, but I really don't find this guy to be too important. All right, I'm coming up on the 15 minutes, so let me stop. All right, guys, I am back. I just texted Mr. Kirkby because this is the program he uses, and I just can't picture him being okay with being stopped at 15 minutes. So I must be doing something wrong here. So I want to do one second derivative test problem with you guys, even though I hate the second derivative test. So I skipped the other note sheet, not the other note sheet, the other example. You guys can try that one on your own. And I'm going to walk you through the second derivative test question. So find and classify all critical points using the second derivative test if possible. Okay, so that means I do need to find both the first and the second derivative. So 15x to the fourth minus 15x squared is the first derivative, and the second derivative is 60x cubed minus 30x. Okay, so first I want to find the critical points. So that's the first derivative. So 0 is equal to, I'm going to factor out 15x squared, and I'm left with x squared minus 1. So this means I have critical points. This is difference of two squares at 0, 1, and negative 1. All right, so if I want to use the second derivative test, I now need to take f double prime. I'm going to put it over here. 60x cubed minus 30x. Now, I always prefer to look at factored form. This is a preference here. Actually, because we're plugging in such easy numbers, you don't even really have to do that here. But I will look at it in factored form. This is 30x squared. No, 30x. Okay. So if I take out 30x, I'm left with 2x squared minus 1. So let's talk about it. If I'm using the second derivative test, I have to look at f double prime of 0, f double prime of 1, and f double prime of negative 1. And all I care about are the signs. So we know that these are critical points. So the only place on this function where maxes and mins could occur are these 3 points. So if I look at the sign of the second derivative, it's going to tell me the concavity. So if I look at and I plug in 0, this is, so right away inconclusive. 0 times anything is 0, so I'm done. If I plug in 1, that's positive times a positive times a positive gives me a positive. So remember, this is concave up. So we have a relative min at this point. If I plug in negative 1, that's negative times a positive is a negative, so it's concave down. So we have a relative max at this point. However, the second derivative test failed me here. I still don't know what's going on at f double prime of 0. So I need to just now come back to the first derivative test, which is so silly. So now let's plug in something to the left and to the right of 0 to see if it is a max or a min. So if I plug in negative 1, that's a positive times a negative times, plug in, times, I can't plug in negative 1 because I get 0. So let's plug in like negative 3. Negative. All right, so that is going to be positive. Am I correct? Why do I have a different answer on my answer key? If I plug in negative 3, negative, positive. Oh, so it's going to be positive. Okay. And if I plug in positive 4, doesn't really matter what I plug. Oh, you know what? It does matter. See, this is why I hate this. So this is 1, and so you still kind of need these guys on here. So you need to be plugging in something. Geez, way to go, Bucko. All right. You need to be plugging in something in between the critical points. Let's plug in like negative 1/2. That's what I have to plug in here. This is why I hate the second derivative test. Negative, positive, positive. So this is going to be negative. And if I plug in positive 1/2, I once again am negative. So this is neither, so all that work to find out this is neither a max or min. So I hope I proved my point to you that the second derivative test exists. It'll tell you whether or not your critical points are maxes or mins just based upon the concavity. But again, I don't love it that much. It's beautiful. What do you want me to say? But it's there. We can use it. It doesn't really come up all that much. So now if you look at your notes, we kind of have some multiple choice questions. And I'm on the fence. Do I want to do these with you guys, or do I want you to try these? All right, here's what we're going to do for the rest of the class. I want you guys to finish that other example that I skipped. So make sure you do everything in there. So let's go back and look. Is this the one no, which is the one I skipped? This one. So find the critical points, intervals for increasing, decreasing, second derivative critical points, intervals for concave up and concave down, and any points of inflection. And then I want you to try these four, is it four? Yeah, these 4 multiple choice questions. I just want to point something out to you. If you're ever doing multiple choice questions and you get like something that's like number 80 or 81 or in the 70s, that's from the calculator section of the AP exam. You do not need a calculator, I think, for this first one, but I do think you're welcome to use a calculator on this guy, because who the heck knows what e to the negative sine 2x looks like, because I don't know. So anything with a really high number for multiple choice is a calculator active question. But 19, that's no calculator. Oh, 87. You could use a calculator here. Again, I don't think I did. Let me look. No, there's no way I used a calculator on that problem. So the only one you really need a calculator for is 81 here. I think I'm going to create a Google form for you guys to just type in what you think your answers are so I can see how you did. All right, so that's what we're doing today. You watched your videos, and now you're going to do the example that I skipped, and you're going to type your answers into the Google form. Alrighty, guys. Adios.